Okay, happy Engineers Day to all of you. Where we were, what was our last topic? We have left section A, advantages and disadvantages of flat slab. It is over, advantages and disadvantages of flat slab. Okay, then today we'll go for a sum problem. Where was it? And today I think you all have got the link for the Engineers Day celebration. Try to join there. And so I'll leave the class maybe before 5-10 minutes. History. Hello. Okay. I scored. History. Okay. I'm using a different laptop, so it is very slow and I could not connect at on time. Is my screen visible to you all? No. Okay. See here, this is a question from your flat slab without a column, head, and a drop. You see here, design an interior panel of a flat slab of panel size 4.5 into 6 meter, which is without providing drop and column head. Okay, see here, these are your given things. Size of the column 300 into 400. These are your columns here. This. Okay, live load is given to you. We have your floor finish is given to you. Height of the column is also given to you. And above and below the slab, yeah, okay. So the use of M20 concrete, you have to use M20 concrete and Fe415 grade of steel. So this is the figure given to you. We have to design these interior panels, okay, which are of size 6 meter. This is the longer span and this is the shorter span, which is of 4.5 meter. This one. And these are simple basic plain flat slabs without drop and without column head. So what we have to do first of all is that we'll find out the depth of the, since we are going to design now the flat slab for this particular interior panels. So what we have to do, we have to find out first of all the depth of the, first step is to calculate the depth. Okay, first step is to calculate this depth of the slab. Now, for the depth of the slab, if we go to IS code 456 here in your page number 53, we'll go to page number 53, 29, okay, 51, 52, and 53. Now here you will see in the page number 53 of IS 456, you will see here these are the provisions for your flat slabs given to you, all these things. So we have to calculate now the depth of the column, the depth of the flat slab. So what is the depth of the flat slab according to ISO? The thickness of the flat slab shall be generally controlled by consideration of span to effective depth ratio given in clause number 23.2, which is in page number 37. Okay, so in page number 53 you will see these are your provisions. What? The thickness of the flat slab shall be generally how much? It should be according to the clause number 23.2. For slabs with drops conforming to clause number 31.2.1, this one 31.2.2, span to effective depth ratio given in clause number this 23.2 shall be applied directly. Otherwise, the span to effective depth ratio obtained in accordance with provision in 23.2 shall be multiplied by 0.9. Also, so this was your thickness of the flat slab. Now for this, to know this, you have to know the clause number 23.2. What is your clause number 23.2? So clause number 23.2 will be in your page number 37. So let us see what is in the clause number 23.2.1 in page number 37. This is page number 37. Here now you will see in the clause number 23.2.1, this one, what I just mentioned, the basic values of span to effective depth ratios up to 10 meter is how much for cantilever, it is how much 7, for simply supported it is 20, and for continuous it is how much 26, and we have a slab so which is a continuous, which is continuous, so it will be how much the effective depth ratio, the span to depth ratio will be equal to 26. Okay, so now if you go again, go back to your this one, the problem. Here the first step in the designing of this flat slab, simple flat slabs, what you have to do, you have to calculate the steps. So here you will see the, according to clause number 31.2.1, what was that? The span to depth ratio should be equal to 26 for your this one continuous. Wait 1 minute. Okay. So the first step was what? The depth of the slab. So according to clause number which I showed you in page number 53, clause number 31.2.1. So what was there? The span to depth ratio should be equal to 26 for your continuous beam, but when there is no drop, what happens? It will be multiplied by this span to depth ratio will be multiplied by 0.9. If you go again back to the IS code, here from this clause we got the values of the span to depth ratio. Span to depth ratio up to 10 meters, for our spans up to 10 meter. What we got? The span to depth ratio for our continuous this thing was how much? 26. Okay. So again if we go back to page number 57, sorry 53, okay, 52, IS code page number 53, here we have come back to this clause now, which is the thickness of the flat slab shall be generally controlled by considerations of spans to effective depth ratio given in clause number 23.2. Okay, so 23.2 we got from unitary point to the values of span to that ratio. Now what it is mentioned here, that the slab width drops conforming to 31.2.1 this 2.2 span to effective depth ratio given in this clause 23.2, which we saw the values of span to depth ratio shall be applied directly. Okay, otherwise when there is no drops, slabs with drops, there is no drop, then what we do, this span to effective that ratio obtained in accordance with the provision in 23.2 shall be multiplied by 0.9. Okay, for this purpose the longest span will be considered, and remember this thing, the minimum thickness of the flat shall be 125 mm. Okay, this is the minimum thickness of the slab which you must take, flat slabs 125 mm. Now going back again to the problem, if you see here, flat slabs, the depth of the slab we got L by D was 26 for your continuous. So L by D is 26. Now we have to multiply this 26 with 7, sorry, with the with a modification factor. Why? Because according to clause 23, according to clause number, this thing in page number 37, the clause number 23.2.1, which we have seen, there we got the span to depth ratio to be 26, right? But then we know from clause number 31.2.1 in page number 53 that this span to effective depth ratio should be multiplied by 0.9. Okay, so 0.9, but this 26 value which was given for continuous L by D ratio was 26 should be multiplied by modification factor. Why? Because since we will multiply this L by D with 0.9, here if you see in I school it is mentioned that to be shall be applied ideally, otherwise the span to effective that ratio obtained in accordance with this shall be multiplied by 0.9, right? So since we don't have the drop in this problem, so we will be multiplying our span to depth ratio with 0.9. So this L by D will be multiplied by 0.9, and as a this compensation here with the value of L by D which was provided in the clause number 23.1 2.1, we are going to multiply a modification factor. Now what is your modification factor? For that again we have to go to page number figure 4 of IS code, page number 38 or 36 it was. This is your page number 53. Okay. This is page number 34, 35. Yeah, here was our clause 23.2.1, which we got continuous 26 value span to depth ratio. Now so what is our modification factor? We will get our modification factor from this figure. Okay. Let me put my charger. So for modification factor, what you have to assume a percentage of tension reinforcement. Okay. So this one here are the on the x-axis it is given all the percentages of the tension reinforcement, and if we assume so in the problem if we see again here we have assumed the percentage of steel to be 0.4%. Okay, now if we assume 0.4%, this one 0.4% here, then with respect to this 0.4 percentage of reinforcement you have to also we'll get a modification factor with respect to this, but also we need to know which fs curve we are going to consider with this 0.4 percentage with 0.4 percentage of steel. Okay, so now what is your fs? Fs is your 0.58 into fy. This is the value of fs given to you here, which is 0.58 Fy into area of the cross section of steel required, area of the cross section of steel provided. So since we are assuming it to be 0.4 percentage of steel, so we will assume this steel required, this one, to be equal to the steel provided. How much is required, that much we are providing, we will assume, and so this portion will become 1. So Fs is how much? 0.58 Fy, because we consider this two to be equal. Steel required is how much, steel provided is how much is required, we have given that much, it's provided that much. So 0.58 into Fy. Now what was our Fy? We know it was given in the question, Fe 415, this one mentioned to you in your question, use M20 concrete and Fe415 steel. So we know our Fy value. So we'll get this value, Fs is equal to, that means 0.58 into Fy. So this will come to be somewhat 240.7. So that means this is your Fs value. This one, Fs 240. So we are going to consider this curve here, and then with respect to this curve, with respect to this 0.4 percentage of steel, we will see FS 240. So if you see it is coming somewhere here, so let us consider it to be 1.3, 1.3, 1.4, 1.5, 1.6. So we will consider this to be, it is here somewhere, so 1.3. Okay, so now what will happen? 1.3 is our modification factor. So you will see here now this one. After assuming what we'll have, this is a bit wrong. Okay, here. So what you're going to do, just note it down. You will have here, if I mark it here with my pencil, it will be here how much into 0.9 equal to 26 into modification factor. So your depth of the slab we will get from this equation. Okay, now why? Because your span you know, but you don't know your depth. So we are going to assume some depth for our design of the flat slab. So find this thing. How we can now we can place the values. Modification factor, we just now we have found the modification factor to be 1.3. This one from this table, from this graph, this one from this graph, if you see, we got 1.3. So this one, once you put the values, you will get your d. Calculate, just calculate the depth value from here. What is your depth? What is coming? Because this was wrong here, 0.9 was not multiplied. But you people do with this, calculate this. How much is your d effective depth? Calculate and say how much. Your d value how much? Span you already know, this is the longer span is given to be 6000 in your question. How much is d? Anyone? 159.76. And others? Because I don't have this calculation part. This is wrong here. How much? Others 159.76. Okay. That means it is 159 point. You have got your this d value now here. D is equal to 159.76. So we can consider this, since we are assuming this is the effective depth. So the overall depth, we can consider the overall depth D, we can consider it to be 200 because we got 159.76. So we can consider it to be 200 mm. Since we're designing, we'll take a greater depth than what we have got the effective depth here. Okay, so let us assume our overall depth here to be 200 mm. So this was our how we can design the depth of the flat slab from the IS codes with the use of IS codes. Okay, so next step what we are going to do is, the first step was your depth of the slab, to find out the depth of the slab. Now the next step is to calculate your loads. This one. The next step is to calculate the load, and you know the live load was given to you 4 kilonewton per meter square in your question. the floor finish was given to you 1 kilonewton per meter square. Self weight of the slab was also given to you 0.2 into 25. Self weight of the slab, why? Because 200 was our depth. We have assumed our depth to be, we will be designing for 200 depth of the flat slab. So this depth into our unit weight of the concrete. So we got our self weight of the slab to be 5 kilonewton per meter square. Okay, so the total dead load will be how much now? This one floor finish plus our this self weight 5. So total is 6 kilonewton and the life load was 4 kilonewton. So the total is 10 kilonewton. Now what will be the factor load? We all know, multiply by 1.5 and we get our this thing 15 kilonewton per meter square. Yeah, okay. So this is our total factor load which we have got according to our slab depth also, the total load including the self weight. How much is our total load? 15 kilonewton per meter square. Okay. Now the next step what we are going to do is, okay, the next step if we see is our stiffness calculation. Calculation of stiffness. Now what is the calculation of stiffness here? Alpha C. Along the longer span, we are going to check the alpha C value. Then along the shorter span, we are going to find out the alpha C value, because alpha C value we will get also from the IS4. But according to our design, how much is our stiffness, the relative ratio of the stiffness, we'll find out. Okay, such that we will that will help us, this alpha C value, this one will help us in calculating or finding out whether we need some corrections for pattern loading or not. Okay, so in your calculation third step you will see uh, alpha C, how to calculate alpha C. Alpha C is what? Alpha C is nothing but the ratio of the stiffness, relative stiffness. So we will find out the stiffness of the slabs and the stiffness of the column. Okay, so what is the stiffness of the relative stiffness of the slab? It is given by 4EI by L, stiffness 4EI by L. And what is your all these things, along the longer span, your L is 6000, your I is what? BD by 12. So BD by 12. D is our, we know already. B is this much because along the longer span, since we are checking. Okay, our meeting is going to end in 5 minutes. I'll do one thing. I'll start from the third step from the from 1 p.m., which is our next class. Okay. I think because I also have to join now on the meeting, another meeting. I'll take the attendance on the second class when we have from 1 p.m. I'll take the attendance and I'll give that. Okay. I'll give those attendance from for both the classes. Okay. Fine. Okay. Okay. We have another meeting now. So I'll just, we'll meet at 1 p.m. and we'll start with the third step from the third step. Okay. Okay. Thank you.